So first of all, we're going to look at a graph and see exactly what do I mean by infinite limits. So this graph right here is the graph of 1 over x minus 1 squared. So we know that x equals 1 is going to be a vertical asymptote here, right? Because 1's not in the domain. We can't remove that discontinuity, so it's a vertical asymptote. And I see from this graph that it's going to positive infinity from both the left and the right. So if we write that using limit notation, sorry about that. So the limit as x goes to 1 of this function does not exist. We already know that. That's what happens when we get a number divided by 0. However, if I look at it as the limit as x approaches 1 from the left, we're going to positive infinity. And if I look at it as I approach 1 from the right, we're also going to positive infinity. So instead of saying does not exist, I can say that the limit as x approaches 1 in general, since both of these are the same, is infinity. So this limit still does not exist. Remember, a limit is a finite y value, and infinity is not a finite number. It's a behavior. It means we are approaching something that's getting larger and larger and larger. But being more specific about than saying does not exist, I can say the graph is going to positive infinity for that vertical asymptote. Let's look at another function. This one is negative 1 over x minus 1. So once again, I know that I'm going to have a vertical asymptote at x equals 1 because 1 is not in the domain and it's not removable, therefore it's going to be a vertical asymptote. But when I look at this, if I come at it from the left, I'm going to positive infinity. If I come at it from the right, I'm going to negative infinity. So if we go back to one-sided limits, I'll say the limit as x approaches 1 from the left is positive infinity. The limit as x approaches 1 from the right is negative infinity. So if I ask you for the limit as x approaches 1 in general, do those two things match up? No. So in this instance, I'm still going to say does not exist because the left and the right didn't match up. The one-sided limits give me information about the graph and what it's approaching, but in general, I still have to say does not exist. Okay, so to be able to figure out which ones are vertical asymptotes, we need to go back over what's a vertical asymptote versus what's a removable discontinuity or a hole in the graph. So, for this first function, what can x not be? What's not in the domain here? X can't be negative 1. Can I remove that? Does it have anything in the numerator to simplify out? So we have a vertical asymptote at x equals negative 1. The second function, a little more complicated. If I factor my denominator, it's a difference of squares, and I'll get x plus 1 times x minus 1. Can I factor the numerator?
Yes.
No. Why not?
It's not a difference of squares.
Because it's not a difference of squares, right? There's a plus in between there. And so I can't do anything with that. You might be tempted to say it's this. But if I multiply that back out, that's x squared plus x plus x plus 1. That's not the same thing. Right? So unless there's a minus in between it, it's not a difference of squares. So I can't do anything with it. So now for this function, I've got two values that x can't be. They're not in the domain. And neither one of them is going to cancel out. Right? Because I can't factor my numerator, so there's nothing to cancel out. So I have vertical asymptotes where? X equals -1, x equals +1. Okay, cotangent x. Well, cotangent is equal to what?
1 over tangent.
Okay, and what is tangent? Sine over cosine. So the reciprocal of that is cosine over sine. So we're looking for when is the denominator equal to 0? So we need our unit circle here. So looking at the unit circle, starting over here, what is that angle? 0. And sine of 0 is 0, right? When is it 0 again? Okay, if we keep going around, when is it 0 again? Okay, so how do we write that in general? N times pi. Any multiple of pi, sine is going to be 0. I can't cancel it out. So all of these are vertical asymptotes. And if you think about the graph of tangent or cotangent, they're both very similar. It looks like that repeating, and for every period there's a vertical asymptote in between it, right? That's actually tangent. I think cotangent goes that way. Okay, what about this function? In order to figure this one out, first of all, we know x can't be what? -2 or 2. How do I know that? The denominator is a difference of squares, right? But in order to determine if those are wholes or vertical asymptotes, we need to factor the numerator as well and see if anything will simplify out. So what multiplies to -8 and adds up to 2?
4 is -2 and 4.
Try again. Adds up to +2.
4 is -2.
+4 and -2. And then we said the denominator was a difference of squares. So the factor of x minus 2 is going to simplify. So x equals 2 is a removable discontinuity because we just removed it. We simplified it. And I ran out of room. And x equals -2 is then what? Vertical asymptote because we couldn't remove it.
So x equals 2 is the whole?
Yes. However, the correct terminology for a whole is that it's a removable discontinuity. And so when you go to put this into WebAssign, you're going to classify, and it's got a pull-down menu that either says removable or non-removable. So that's the vocabulary Webison's going to use. So it's the vocabulary I'm trying to use now, even though it's just a whole. But that's kind of like slang in terms of math. Okay, so there's a trick that I use to find these infinite limits. Okay, and not every limit that we're going to do today is going to result in positive or negative infinity. Some of them are just going to work, right? Just like when I talked to you about doing direct substitution, and I said some of you are going to go straight to wanting to factor or do whatever. Sometimes it's just going to work. In this case, it's not going to. Okay, the limit as x approaches 1 from the left. First thing we try is direct substitution, and we get 1 minus 3 over 0. So that's a number over 0. It's got to be a vertical asymptote, right? So we have to decide what kind is it? Okay. The way I like to do this is to put whatever my function is in factored form if I can. I didn't do it because it was going to cancel out. We knew it wasn't going to cancel out because we got a number over 0. We didn't get 0 over 0. But I like to put it in factored form because I don't want to plug this in my calculator. Okay? A number to the left of 1 on the number line would be like 0.9. And if you wanted to, you could plug 0.9 into the original expression back up here and see if you get a positive large number or a negative large number. But we know it's going to either positive or negative infinity. So all I really have to determine is what is the sign of this thing with a number that's a little bit less than 1. Well, bringing this down here, if I were to plug in a 0.9 into x, that's a positive number. If I plug in 0.9 to x minus 3, do we get a positive or a negative number? And if I plug in 0.9 into the denominator, do I get a positive or negative number? I get a negative. So positive times a negative in the numerator is negative, divided by a negative. That whole number, whatever it is going to be positive, right? So this one's going to positive infinity. Okay, if you don't like my method, you pick a number a little bit smaller than the number, or since this one's from the left, a little bit smaller than 1, plug it in the expression, do the calculation. But it's very time consuming, they're ugly numbers, they're decimals. This, to me, is easier. You put it in factored form, figure out if all of the factors are positive or negative, and then I know where it's going. Now, you can also check these on your graphing calculator. You should. But when I test you on it, I'm going to want to see how do you know other than from the graph. Okay, if we look at it from the right, then we want to pick a number a little bit bigger than 1. So now we're over here on the number line. So let's say 1.1. If I plug that in to x, that's a positive number. If I plug it into x minus 3, so 1.1 minus 3, that's a negative number. And if I put 1.1 in the denominator, that's a positive number. So is this thing going to positive or negative infinity?
Negative.
So if I asked you for the limit as x approaches 1 in general, what would you have to tell me? Okay, if I do a direct substitution on this problem, the limit as x goes to 0 of 1 plus 1 over x squared, we get 1 plus 1 over 0. Now, we've already said that a number over 0 is going to go off to positive or negative infinity. And if this thing here is some huge number, then the 1 is insignificant compared to infinity, right? So we're not worried about this 1. We're only worried about the sign of our 1 over x squared term. Now notice I didn't ask you for a one-sided limit on this one. My numerator is 1, so it's positive. My denominator is x squared. So whether I come for the left or the right of 0, when I square it, it's going to be positive, right? So I don't need to worry about the left and the right if I'm thinking in these terms. When I square it, it's going to be positive no matter what I do. So this is going to be a positive infinity. Now, if I didn't recognize that that was going to be positive no matter what, I would have had to check from the left and check from the right and see if they matched up. And they would, right? Because we're squaring it whether it's a negative 0.1 or a positive 0.1. But since I saw that, I don't have to check left and right. I know they're both going to behave the same way. Okay, we already talked about cotangent being cosine over sine. So this is the same thing as the limit as x approaches 1 from the negative side of x squared plus 1 over cosine of pi x over sine of pi x. So we're going to flip that fraction and multiply, right? And I've already gone against what I said to you guys, which is sometimes you just want to plug in and see if it works. But I knew where I was going with this. In order to evaluate cotangent, for me, on the unit circle, I got to break that down into sines and cosines. So now we're going to try a direct substitution here and see what happens. So for x squared plus 1, I get 1 plus 1. Sine of pi is 0, and cosine of pi is negative 1. Well, 0 divided by negative 1 is still 0, right? It wasn't an infinite limit problem. Now, does that problem have any vertical asymptotes, that function? Yes, just not at 1. Right? Because it is possible for our denominator to be 0, but it's not going to happen at 1. Okay? Here, if we plug in 0, we're going to get 0 plus 1 over 0. So, since it's not squared like it was in the other problem, I have to determine if that's going to be a positive or a negative. So we're not worried about this first 0, that's just 0. We're worried about the 1 over x. So the 1 in the numerator is going to be positive. In the denominator, we're approaching 0 from the left, so that's a number a little bit less than 0. So is my denominator positive or negative? It's negative, so is this one going to positive or negative infinity?
Why is that negative instead?
Because a positive number divided by a negative number is negative. 1 is in the numerator, which is always going to be positive. In the denominator, we're doing a number from the left of 0, that would be like negative 0.1. So our denominator is negative. And our first term here didn't matter because it was just 0. Okay. For natural log, if we plug in 0, we have a problem. Because 0 is not in the domain of natural log. Natural log is the inverse of an exponential, so it actually does something like that. Natural log says e to the what equals x, right? That's how I write it in exponential form. And there is no exponent that is ever going to make e, which is a positive number, into 0, right? I can raise, it's 2.71 something. I can raise that to any power I want to. I'm never going to get a negative number, and I'm never going to get 0. Those aren't in the domain of it. So I can't just direct substitute the 0 in there. What I can do is graph it. And I see that if I know the graph coming from the right towards 0, I'm going off to negative infinity. So when you see natural log problems with limits, first you want to try direct substitution. When it doesn't work, you want to look at the graph. Okay, for this one, coming at 8 from the left, if we direct substitute this in, I'm going to get e to the 8 over 0. Now my numerator is always going to be a positive number, right? 2.7 something raised to the 8th power. That's a positive number. 8 from the left, let's put that on the number line. I'm very visual about this stuff. Would be something like 7.9. 7.9 minus 8, that's a negative number. And if we cube a negative, we still get negative. So this one is going to negative infinity. Again, you can verify these by graphing them, but you have to be good at using your graphing calculator and know when to use parentheses. Okay, if I try direct substitution on this, when I plug in a negative 3, we're going to get negative 3 plus 4 over negative 3 squared would be 9, minus 3 minus 6. That's 1 over 0. So it's going to be a vertical asymptote. We have to decide what the signs are. So I'm going to factor my denominator. What multiplies to negative 6 but adds up to 1? Positive 3 and negative 2. Okay, so now that I have it factored, I can just do my little sign notation thing instead of plugging in an actual number. So, my numerator is going to be positive. It's going to be positive 1, as a matter of fact, but it's going to be a positive number. If I plug in a number to the left of negative 3, and this is why I use the number lines, because without a number line, when I'm dealing with negative numbers, I tend to pick from the wrong side. From the left of negative 3 would be like negative 3.1. So this is going to be negative. And if I plug in negative 3 to x minus 2, we're also going to get a negative. So is this thing going to positive or negative infinity? Positive infinity.
So you only do that when there's a vertical asymptote?
Yes. Right, and the way I knew